the concept behind is actually quite different from these two point of view. But in the end of the day, both are still helping you in getting the probability outcome of your random variables. All right. So these are all the recaps that we have from the probabilities notation. If you still recall at the beginning, we talked about what is probability and also those basics, including complements, including multiplication rules, and so on. Then we have base theorem. So we have gone through last week's class. I know that some of you are still having doubts maybe for some of the questions, but I tried my best after the class to answer all of you. So if you still have doubts, in that case, please send a chat and tell me what is your doubt so that I can actually further explain to you if possible. Okay. Then discrete random variables. Okay, this week you're gonna go through this class, so make sure that you have again attempted before you are coming to the class. We have two main calculations over there, which is binomial and also Poisson. Of course, Bernoulli is considered part of binomial as well. It's like a special case of the binomial distributions. So these two are the main calculations, but of course the concept that we actually talked about before the class is also important, right? Now we move on to the continuous random variables. So the continuous random variables can take any value within a range of values. Okay, so we usually given maximum or minimum values, right? And is everyone muted because I can hear some background noise? I just double check. Just mute everyone. All right. So if a variable can take any value between its minimum and maximum value, it's called a continuous variable. So when we flip a coin many times, for example, 10 times, and we compute the average number of hits per flip, all right? So average number of hits per flip is a result from a random process is flipping, result for a random process, flipping a coin. So in that case, what is the possible number for your average number of hits per flip? Imagine if every time, in one case, okay, in one possibility, every time you're flipping a tail, you're not flipping a head. So every time you're getting 0, 0, 0, 0, 0 for the 10 times. Another extreme, you are getting every time or once, okay, because heads basically heads, and then you consider it's 1, so it's 1, 1, 1, 1, 1, 10 once. So they are actually two different extremes, and when you calculate the average between these two extremes, one of the extreme is 0, and another extreme is 10, right? Because you are calculating, in terms of number of hits and also number of tails. And then when you are trying to do the average, because you are dividing on your occurrence, so 0 divided by 10 is 0. Okay, maybe I try to do some drawing. 0 divided by 10 is 0, and then 10 divided by 10 is also 0. If this one number of hits equals to 0, this one number of hits goes to 10 trials. Okay, so in that case, you know that this one, your average is 0, this one, your average is 1. And this basically is your range, your minimum range and also your maximum range. Because your average value over here can take between 0 to 1, okay? And it can be any values. Of course, in here, because our trials is only 10 trials, so you might argue that, oh, the possible outcome is only 0.1, 0.2, 0.3, 0.4, 0.5, and so on. So in that case, if you follow this explanation last week on discrete random variables, this can be discrete because we know that it's a bounded outcome, right? The so-called bounded outcome as in, oh, it's between 0 to 1, and then I can count that all the possible outcomes 0.1, 0.2, 0.3. This is because you know that you have, at the beginning, you already know that how many is your number of trials. In general, we put this so-called 10 trial is actually n. You don't know what is the number of trials. And when you're changing your number of trials, your whole range, although it doesn't change, because number of trials when you are changing, like for example, you change to 15, then this one can be 15 as well. Sorry, 15. So your maximum and minimum won't change, but the possible values in between is actually changing. Like right now you can become 115 and then 215 and then 315, all potential values coming out. And then so in that cases, you'll notice that the whole outcome over here is actually range between 0 to 1, and any values between these 0 to 1 can be the possible outcome for your random variables. That's the reason why we consider as a continuous variable over here. Okay, rather than the discrete random variable, we are very sure that about the outcome itself. Then, of course, the clear example over here for discrete random variable is actually number of heads. Number of heads is a clear discrete random variable because it can be only 0 to 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, no other outcome anymore. But when you are calculating average, and this average is now your new random variable, you become continuous because it can be any value between your range. Okay, because if it's I forgot my mouse. Okay, so if this you're considering the random variable of number of heads, if you're changing n to 20 or 30, it's still giving you a bounded outcome because you still know that, okay, when you are changing n to 20, then it's 0 to 20, and then every time it's step by 1. So it's very clear that your outcome is going to be discrete. Okay. So this one is a general statement over here. The average number of head per flips can take on any value between 0 and 1, and even a non-integer value, and therefore it becomes a continuous random variable. This one is just a further explanation on this. Okay, just to make sure that you are very clear on this part. Then, the probability distribution of a continuous random variable is represented by an equation called a probability density function. It's different from a probability mass function that we have in the last class, if you still recall, when we are actually having something like a histogram, okay, to tell about the probability mass function, or I also show some example that maybe you just have a stick view, okay, so it's possible. But this one, density function, is going to be something like a curve, and the main thing over here is for you to calculate the area under the curve. Now things comes in. Oh, I didn't put it over here. Later on, when we check the notes, then you know. Because the main thing about calculating area under the curve, you still recall your, I think, Form 4 or Form 5 classes, is eventually you are doing an integration on the function that you have. When you are doing integration on the function that you have, you're calculating the area under the curve over here. Okay. So there are two equations over here that you need to be aware of. Main equations, but of course there are some probability you need to cater as well. But this one is for you to calculate the probability between minimum range to your maximum range for your x variable. Is equals to the integration of function x. Function x basically refers to this. Okay, this is the function x. Later on, you have a big F and also a small f. Small f basically refers to the probability density function, but big F basically refers to your cumulative distribution function, CDF. Okay, and then when you are actually integrating calculating based on a range, so your integration basically also follows your maximum limit and minimum limit. Maximum will be D, minimum will be C. So it's coming from here. Okay, so just draw a line. Okay. Actually, this one, if you are very familiar with integration, then this class is actually quite easy for you. You just need to know when to apply what kind of formula. Okay, and then expected values. Expected value of EX equals to integration of BA. Of course, we don't really have any BA over here. That's why we just put BA. But of course, you can follow CD as well. Okay, and then X, FX, EX. So notice here, this is the difference. FX and also X, FX. You are actually times the X over here to the probability function that you actually have for every single values of X. Okay. Over here is actually, I mean, when you're calculating expecting value, you're covering every single possible outcomes. Okay. Later on, when you go into the question, then you have a clearer idea. But eventually, assuming is actually this one is actually all your possible outcomes, and you cut off over here, then this one will be 3 and then -3. Okay. Of course, you don't really have negative outcome this time. Okay. There are some properties of things that you need to be aware of when you are calculating probability density function, where the random variable y is a function of x, which is y equals to fx. So this one is clear cut. You know that this function basically tells you the, there's another random variable so-called y, which is a function of fx. Okay, so it's basically your y-axis. It's the same thing. Then the value of y is greater than equal to 0 for all values of x. The main thing over here is you wouldn't get a graph something like this. Okay, you wouldn't have here, because remember the first thing about probability is it's always bigger than 0. Okay, because you are measuring measuring the chances for it to happen, so you won't get any negative value, or -2 and so on. Sorry, 0.1 or 0.2 and so on. No, so you won't get this kind of curve. Your curve is always up. It's always up. All right. And the total area under the curve of the function is equals to 1. Why is it total area under the curve of the function is equals to 1? It's because if you still recall the total probability rule, when you sum up all the exhaustive events that you have in your potential outcome, for example, when you sum up all the probability for your dice, for your dice to happen, for example, from rolling 1, rolling 2, rolling 3, so for your dice example, so it's 1/6 plus 1/6, and then you basically plus all the 1/6 equals to 1. So when you plus all the possibility that potential outcome in your particular random variables, basically based on your sample space, and you get back your probability equals to 1. So same cases for your continuous probability distributions. When you integrate based on the total area under the curve, basically you calculate all the potential outcome over here, and then it will become equals to 1. It's one thing that you need to take note. Basically, I'll click this one as well. It's quite different from the discrete random variable. Why? This one. If you still you're checking this title over here, it's actually quite a common way for you to calculate one particular value in your discrete random variables. For example, you want to get what's the probability of x equals to 3 when when I'm rolling a dice, and then the outcome is actually 3. Okay, so in that case, all I know is 1/6. Very direct, very straightforward, right? But in continuous distributions, in continuous probability distributions, the answer is always 0. Okay, why? Every time when you are calculating on a particular one value only on your probability, on your random variable, the outcome will be always 0. Means that probability of x equals to 3, 0. Probability of x equals to 4, 0, and so on. Why? Because with a continuous distribution over here, there are infinite number of values between two data points. But if you have only one data point over here, okay? When you have only one data point, you won't be able to estimate the potential range, okay? Any potential values between one data point. Between one data point from 1 to 1, basically is 0. You have nothing over there. So as a result, the probability that a continuous random variable will assume a particular value is always 0. If you feel that this one is difficult for you to understand, then you imagine this situation. You imagine a book, okay? You actually want to calculate maybe the thickness of the book and so on, okay? Or the volume of the book, okay? The volume of the book. So you basically need to measure weight, height, and length, width, and height. And then imagine your height or thickness over here is actually 0. 0, yeah? So the volume of the book will be 0 too. How will you get 0 thickness? Your starting point and your ending point is the same. Okay, basically it's here. Your starting point is 3, your ending point is also 3. So in general, when you are calculating a probability distributions, recall it, when you're actually having things like this, okay? Like for example, it's 1, 2, 3, and so on. When your starting point is 1, when your ending point is also 1, you won't be getting any answer. You won't be getting any values over between 1 to 1, and then you'll always get back 0. But if you have starting point 1, and then you have ending point of 2, okay, then you basically are able to calculate all the potential values between this area, this range, and then using area under the curve, you'll be getting a probability value of 0 point something from here. Okay. So there are some. Sorry. Okay. So there are some probability that you need to follow over here. The first thing is the probability of probability 1. This range, okay? The probability of A is more than W. Okay, now we are using W, but you can use X or Y. I just try to use different random variable to tell you that, okay, that particular algebra is not that important, but you need to know that is the random variable. Then this one, now you notice that it's actually the big F over here. The big F is actually trying to tell you that this is a cumulative distribution function, okay? If you still recall, cumulative distribution function is a bit different. If your fx is like this, then your big fx will be something like this, okay? Because you are basically doing this one is PDF, this one is CDF, and then we consider it's a big fx over here. Okay, so sorry, apologize for drawing, but roughly you can get the concept. Basically, CDF is a cumulative outcome, a cumulative curve. Okay, whenever you are actually from 0, starting point of 0, then you sum up, you try to match the things over here. Okay, and then you continue to sum up, then you get up this. Maybe not like this. Okay, my curve is not so correct. Maybe it's something like this or something like this. That makes more sense. So whenever you are actually calculating a range of it, okay, you are calculating a range of A to B. If you are using CDF over here, okay, 1, 2, and 3 over here, you can actually calculate, because assuming the stopping point is around maybe 0.5. I can't see any 0.5. Okay, so in that case, if you want to calculate a range between 1 and 2, okay, you can actually calculate the cumulative over here, and then you calculate the full cumulative over here. Okay, maybe I cross like this. Maybe I delete it and redraw it better. Okay. Okay, now. Something like this, yeah. Maybe the starting point is 1 is easier for me to explain. Maybe then 2, and then 3, then 4. Okay. So your range, your total range for your probability is roughly over from 1 to 4 like this, and then you want to calculate from 2 to 3, for example. Okay. So in that case, this property basically tells you that you can actually calculate this particular range. Previously, we only have like this 1, 2, 3, 4, like 1, 2, 3, 4. We basically need to do integration over this particular range to get this outcome, right? Okay. Another way is following this example. When you're using CDF this time, you can calculate the small part first. Okay, this small part refers to this one, and then you calculate a big red part, which is this. 1, 2, 3, 4, 5. Okay, so this red part refers to B. Okay, upper limit. So when you are calculating the upper limit of your cumulative distribution function, so you get all this, as well as this one, you get just small part of this. So in the end of the day, you will be able to get this part, and this part basically will resemble this part. All right. Of course, right now you see that the shape is not so correct, but of course when you're doing CDF, the whole thing will be a bit different in terms of the size, in terms of your probability. Okay, but yeah, so mainly that will be the idea. Okay, you're actually using a bigger portion of your cumulative distribution function minus a smaller portion, and then you get this one, which is the range between 2 to 3. Okay, and it's similar to integration on this. And this one is referred to this one. Okay. Then probability 2. You have actually okay. Probability 2. A smaller than W, small equals to B. You notice that all these over here, of course, the end product is the same, yeah? End product is the same, so it's still integration. But you notice that this one having equal sign, this one no equal sign. This one having equal, this one having equal. This one having equal, no equal, no equal, no equal, and all these are the same. It's trying to tell you that the equal sign or not without equal sign over a continuous random variable doesn't really give you any different outcome when you're doing integration, because the nature of this. The nature of this. Every time even you include or exclude the particular probability distribution, probability value of x equals to certain kind of values, it's always 0. Okay, it's always 0. That's why when you're actually following probability 2, that's why no matter your range, when you define your range is with equation, with equal or without equal, it's always giving you the same outcome of the integration of over, oh my God, the integration over here, right? And the last one, the third outcome, which is probability 3. All right, probability 3 is actually total probability rule over here. And then for you to sum up all the probability distributions, which is like, for example, if you sum up from 1 to 4, I try to use this one, hopefully. Oh, very special color. Try to use this one. This one and until this one. Okay. So for this one, right, for you to go up until here, you sum up all the potential. You integrate. Okay, you integrate and sum up all the probability distribution over here from 1 to 4, assuming that your lower limit will be your 1. Okay, your upper limit will be your 4. Okay, so in that case, once you do your integration, your total outcome will be equals to 1 over here. Right. So this one is a total probability rule that I have explained just now actually. So this one falls into your probability 3. So yeah, we move on to example. Because the slide that I upload right now doesn't have a calculation, I believe. So of course this one I'll upload again as an updated version. But I'm hoping that you have, if some of you actually already tried by yourself, then you'll be able to know right now to check your answer. So to consider a continuous random variable x that has the density function equals to 2x divided by 15 on the interval 1 to 4. Okay, so this one basically tells you the function. Let me change back. Okay, I just visualize the function in a bit random manner because I don't follow the exact shape. But if you really follow the shape, I think it will be because it's 2x divided by 15. So when you still recall your class about your linear, your Cartesian map, then it's supposed to be something like this, okay? Because it's a positive, just 2 over 15, maybe just something like this even, roughly. It's roughly even like this, okay? No curve, but it's a linear line, yeah, okay? But that one just give you some, this one just give you some estimation, okay? So this one basically is your curve, is your line. Interval 1 to 4, this basically tells you that 1, 4 over here, okay? And then this whole thing, when you sum up, you will get probability of 1. You see? Interval 1, 4, 0 elsewhere, right? Calculate the expected value of x. So from here, the expected value EX equals to BA. Oh, actually this BA, right, if you really want to rewrite in a more better manner, this can be actually negative infinity to positive infinity. Maybe this one is actually better. But when you're following this one, negative infinity, which is this one, positive infinity will be this one, for this particular graph, of course. Then later on, x. And then this one is your 2x divided by 15. So your x value times the probability functions that you actually have. This one is a bit similar to when you are actually calculating your your expected value in your discrete random variable, if you still recall. Okay, but from here, we do the integration. Okay, so if you are having difficulties with integration, then I will strongly suggest you to study back your maths. Okay, but I'll just do one round here. So like for example, over here, you are doing 2x squared divided by 15. If you do integration, dx for 1, then it will actually become 2x squared. So this one will be changing. Differentiation is -1, right? So integration is 2x 3 plus 1. Then later on, differentiation is putting down over here, right? So integration, you'll be putting down in your denominator, and then you put 3, but not 2. Okay, this is how you are actually getting this whole thing, right? And then, and then following 4, 1. Why 4, 1 is over here is basically your range, where you need to replace it inside. So this 4, when you replace inside over here, so it's 4 to the power of 3. 4 to the power of 3 is 64 times 2, 128. This one times together, you got 45. And then when you are solving this one, since it's a range, so this one you need to be minus. And then the same thing, this one you also need to pass inside. Then you know that 1 to the power of 3 is 1. 1 times 2, you got 2. And then 3 times 15, you got 45. And then this one you minus, and then you divide by 45, you get 2.8. Okay. So you might start to ask me, why we are doing the probability questions, why you are getting 2.8? You're supposed to get between 0 to 1, right? Remember, right now we are calculating expected value. Expected value is mean, if you still recall. Okay. So whenever it's actually mean, the range is supposed to be based on your random variables range. So it's supposed to be between 1 to 4, but not between 0 to 1 anymore. Okay. So when you want to check your answer, when you calculate expected value, you're supposed to double check. Okay, the one that you calculated, is it that we lie on the range between 1 to 4? Means it's around over here. Imagine if you are actually getting a values of like 0.5, then it's actually around here. Is it possible that this is actually your mean? Okay, if you visualize it in this way, it's not possible at all. Right? So this is the example for expected value. Then we move on. Consider a continuous random variable x that have the density function equals to 2x divided by 50. Oh, sorry, same questions. Calculate the probability when x is larger than 2.5. Okay, it's the same question here. It's just that right now, you have a question 2. Calculate the probability when x is larger than 2.5. So from here, you basically rewrite in this way. X over here, larger than over here, 2.5 over here. So again, when you're applying this formula, okay, of course the example that I'm putting just now is D and C, but you can put B and A, you can put anything, but the main thing over here is you know that this one is your upper limit, this one is your lower limit. Correct? So how are we able to solve this one? We don't really have an upper and lower, we just know that it's larger than. Okay? And how am I actually getting this one? Imagine this one is actually, you know that it's larger than 2.5. If you're following this graph again, maybe I draw a new graph. Roughly, yeah. Come on. 1, 4. You want to calculate right now 2.5. Bigger than 2.5. So 2.5 here. So you want to calculate like this. If I draw like this, then you can visualize, right? You are actually calculating between here. Then you'll be very clear that your lower limit is actually 2.5. Your upper limit is actually 4, because your maximum value that you can have for a random variable is 4. So in that case, probably you can actually rewrite it to become 2.5 smaller than x, smaller or equals to 4. Okay. In that case, you'll be covering the all potential outcome from here to here. Okay, so. And then when you are rewriting, when you are solving this equation, then you'll be able to see that, okay, 2.5 is here, 4 is here. And then the function you replace inside, then you are doing another new round of integration. Okay, once you do the integration, then you'll be able to get your answer will be 0.65. I will not repeat again the step for you to do the integration, yeah, but you should know, all right? And then 11, sorry, slide 11. Is there another way? If you still recall that we actually have a property 1, okay? I draw a lot on the property 1, right? If you still recall, there's another way for you to calculate based on the cumulative distribution function. So how are you able to do that? Okay, this is just so-called another way. Okay, it's not wrong that you keep using this way. Okay, because you still get the same answer if you later on when you double check. But the main thing over here is to tell you that sometimes if you know this both ways, it's easier for you to solve certain kind of questions. Okay, you don't need to spend that much time. Okay? So over here, yeah, right now you need to imagine a bit. Imagine a bit as in you are changing your variables. Okay, you're actually putting in another variables, random variables inside this particular fx that you want to calculate. When you want to calculate cumulative distribution function, it's still the same. Okay, it's just that I need to draw it again just to give you some idea. Okay, for you to get, okay, this is 1, this is 4, this is 1, this is 4. Okay, if for those that already get the idea, then yeah, just bear with me for a while. So for you to get this particular, like maybe this one is 2. The concept of cumulative distribution function is always accumulating up. So in that case, right, when you reach 2 over here, this particular value over here supposed to tell you this particular value of distributions. Okay, so in that case, you actually wanted to have this value to get the integration of this whole part. Okay, so this part is your fx, a big fx. This one is your small fx. So you are doing basically an integration based on the value that you're actually choosing. Like for example, if you're choosing 2, then you're actually integrating 2. But if you're choosing 3, then you're integrating 3. Right now, if you're choosing s, okay, if you're choosing s, then basically you're integrating based on s, right? So this s over here can be any value between 1 to 4. Okay, can be any value between 1 to 4. So that's the reason why right now, for me to calculate this part, maybe I try to draw it. For me to calculate this part, which is my continuous random variable. So I will need to do an integration on my original function, which is this one, but I'm actually integrating from s that I'm choosing to the lower limit that I have. Okay, that's the reason why you can see there's an s over here. Okay, and when you are trying to do the integration, the same kind of process, then you'll be actually able to slot in to S2, and then this one you slot in, and you'll be able to get one specific function, okay, just for fx, big fx, sorry, for a cumulative distribution function. So you're basically calculating this line. This whole line over here. So in that case, for you to calculate probability of x bigger than 2.5, which is similar to what I have been writing just now. Sorry. 2.5 smaller than f, smaller or equals to 4. Okay, you can change the way that you calculate to become like this. Now you're replacing 4. Okay, when you're now replacing 4, because just now it's a random variable, right? When you're now replacing 4, you're calculating the whole thing. And then later on, when you change to 2.5, you're calculating from 2.5 to the whole thing, to the minimum limit. And then you can just minus it up, and you get range between 2.5 to 4. Okay, I just tried to draw it again if you're not following. Let me see, something like this. Then 1, 2, 3, 4. Then I have a black pen right now. So right now is this one. You're calculating this whole thing. 2.5, red pen, 2.5. You're calculating this small part of thing. Okay, the big region minus the small region will help you to get the region between 2.5 to 4. Okay, so the rest of the thing, you just apply the formula that you get. You just apply the formula that you get from here and here. But this time, this one is 4, replacing 4. This one is replacing 2.5. And when you solve the equation, you'll be getting 0.65. Okay, so I mean the whole process is almost the same. Not to say almost the same, but this is just that the time that you're doing the integration is a bit different. This one is from beginning. You can solve it in one shot. This one, you are actually creating another equation based on for your CDF. Then later on, you're getting your answer. Because why it's good for us to know these two ways, because maybe the question is not giving you the original PDF function. It can give you the CDF. So in that case, if you are getting the CDF, you can directly apply this calculation to get your answer. Okay, so far so good. Let me see the questions from the floor first, yeah? So why didn't he use the equation x fx dx? Huh? Why here he used the f? Okay, maybe Jun will already answer questions. Yeah. Yeah. Okay. All right. So nothing much from the floor. I continue on the example 2. Okay. This time you'll notice that there's actually ax over here. Okay. Suppose x have a range between 0 to 3. Okay. Now range already given to you, and the probability density function of x fx equals to ax. Calculate the value of a. How are you able to get value of a? If you still recall your property tree, okay, your property tree is actually this one. The probability tree for you to get, for you to get your total probability rule to be fulfilled, your integration of your using the range of negative infinity to positive infinity equals to 1. So in that case, when you're applying over here, integration, which is ax, okay, negative infinity, positive infinity, which is 0 to 3, equals to 1. So this whole thing is one equation, and then you try to solve this thing. So basically, you do an integration over here, which is like this. You get this one, which is become 9a divided by 2 equals to 1, and then you will get eventually 2 divided by 9. So I just skipping the step from here to here, but I believe you are able to do it right now for the integration part. Just becoming ax squared divided by 2, 3, and 0 here. And then you'll be able to go here. Then this one, cumulative distribution function of x. So how are you able to calculate cumulative distribution function? This one is a bit different way for you to rewrite. Okay, just now it's actually when you're rewriting this one, you are replacing this value. This time you are actually replacing another value to become your random variable. Okay, so in that case, when you are changing it, okay, over here, fx x equals to x0 over here. Where is your x coming from? Over here. Where is 0 coming from? From your lower limit. If you still recall the way that you're actually calculating your integration over here. Right? And then AU du, okay? This is because you can't have 2x over here. Or ordinarily it's actually x, right? It's actually coming from here. Right now you need to, not to say imagine, but you need to know that there are 2 different random variables over here. One random variable is for your original PDF. Another one is for your CDF. Okay, that's why right now the way that we are writing is a bit different compared to here, but the main concept is still the same, right? You are still replacing the range, but this time you're using AU over here rather than AX, because you can't use the same variable at 2 places, or else people will think that, okay, these 2 are the same values. Okay, but I mean, or same curve, but eventually it's not the same curve. So the same process will still apply where you do the integration. Okay, of course, you can actually do this one first. Okay, you can actually take out this one. Like for example, if you want to, you can actually make it become x0 u du. Okay, but please be careful. Some of you might make some mistake on if your equation is actually integration of x0 u plus 1 du. Okay, then please don't just take the a outside because here don't have a, you know. If you take a outside, it will become u plus 1 divided by a, not just u plus 1. So this one, when I'm actually marking previous semesters students script, this is the one of the main problem that we are facing. Not so sure why is the student making this kind of mistake somehow, because it's very general, right? You can't just take out like this because this one is just a direct times. That's why you can actually do the taking out. So from here, you got actually getting 2 over 9 from this one, and then for this one, we'll be getting u squared divided by 2, and then this one is x0. That's why you are getting 9 times x squared 2 minus 0. And then the minus 0 is no. You don't really need to write this one, bracket. You know? That's why it will resemble back to this one. Okay. Okay. The way that these two way is different is because actually the main difference over here is the outcome over here. Okay, like this one. When you are using this one as your variable s, okay, and then this one the outcome is actually s, right? And then if you want to rewrite the whole thing, then you actually become fx x equals to x squared minus 115. Okay, I mean, this is the whole outcome that you actually get from this particular equation. You just need to write one more time if you really want to, like to change back this s to x. Okay, but in general, because we are looking at how are we able to represent the particular random variable using x. That's why if you are changing this way, right, you are getting the answer directly. Okay, but changing in this way, okay, on your random variable, you are actually swapping the random variable on your particular PDF. Okay, particular PDF. That's why in the end of the day, you'll be able to rewrite in this way. All right. We continue the example. Suppose x, you're saying calculate the x, probably between x between probability of x between 1 and 2. So this one, you are actually getting this one. And then you might argue that between 1 and 2, maybe you don't include the equal sign, but for the particular continuous random variable questions, include or exclude, you still get the same answer. And it's actually following property 2 is the same. So you don't need to worry too much. And then once you're doing integration, okay, this 2 is actually 2 different ways to solve the problem, you know. So this one, you are doing the integration again, and then you'll be able to get 1 over 3. But this one is using the cumulative distribution function that we actually calculated just now. And then you're just swapping in 2 and 1, and you'll be able to get the same answer over here. Okay. So again, this one is just demonstration on 2 different ways I'm doing it. So that's all. Please try to do more exercise if you are still not please try to do more exercise on this particular tutorial later on. Chen Yi, wow, you got a very long question. Let me finish up the slides, and then later on, because I want to finish it in 1 hour, maybe my explanation is it misleading? Let me see later on. Maybe I'll try to rectify on the question later on. Chen Yi, yeah? Let me finish up this one first. I want to finish out at 10, right? So continuous probability distributions. From here on, I'm actually giving you some another slide, another online resources which is come from Toward Data Science. They actually give a quite good explanation on the basics part, so you can actually follow that one as well if you want to. But in general, I'm actually showing you how the uniform distribution is actually looks like. So based on the range that you have, this one is actually your A and B. Okay, your uniform distribution, minimum range and maximum range, and then you're actually having 1 divided by B minus A. So that's why you are getting things like this. And this one, your CDF, which is things like this, right? This one is measuring probability value itself, okay? This one is cumulative. Okay, why we need uniform distribution is because uniform distribution is useful for you to model certain kind of fixed events. Okay, fixed, not to say fixed event. I mean the events that is actually will happen in a very not to say frequent, but in a uniform or fixed way. Okay, so in that case, the position of read write head in the computer disk request. So this one, if you still if you know how a computer hard disk works, it's basically having a reading disk and it's trying to read the data based on the disk, magnetic disk that you actually have. They actually have a head for you to go down and then actually read the particular data that you actually have. So in that case, right, every time when you're reading it, okay, the position is actually moving randomly. Okay, and this random is following certain kind of so-called uniform distribution. That's why it can model using this one. Okay, usually uniform distribution is for us is for those having almost, I wouldn't say fixed, but fair outcome. Okay, you don't really have a bias kind of situation on that particular potential outcome. Okay, for example, what we have for dice roll. Dice roll is also considered uniform distribution. If you still recall, dice roll is placed in discrete. So that's why you notice that it looks like this for 1, 2, 3, 4, 5, 6, and then this one is 1/6. This one is your probability distribution for your dice roll, fair dice roll. Okay, that's why if you link this all line together, it will become one line. Okay? Same for uniform distribution in terms of continuous. Okay, still one line. It's one line over here. Okay, and then the probability of arrow stops at an angle in the board of spinning arrows. Again, it's the same because it's actually it's somehow like an independent event. You don't really affect by your previous events. That's why it's quite possible for you to land on any single part, any single angle. Okay, but over here, one example over here is you can actually treat it as a discrete outcome as well, because you can change the way that you measure your probability that to become the outcome of getting 1 or 2 or 3 or 4. So in that case, the probability will become 1/4 for every single outcome. Okay, so the whole thing can change. Okay, from continuous where you're actually measuring on the angle, okay, to become discrete where you're actually measuring 1, 2, 3, 4, for example. 1, 2, 3, 4. So it depends on how you want to understand or design your environment, okay, or basically events. Then normal distributions, when you there are two main parameters for you to build the normal distribution, which is mean and variance. Okay, you have studied before, so you can use table or software for you to generate different kinds of probability distributions, which is based on normal, or sometimes you heard it as Gaussian, right? So Gaussian is based on mean and variance. So your mean point basically decide where your peak is, right? So like this one, the mean point is actually, the green line is -2. That's why you notice that it's 2 over here. And your variance is 0.5, so it's gonna looks like this. But if your variance is actually increasing, then you become looks like this one, this color. Okay, this color, which is having a variance of 5.0. So you won't have a very high peak because your data is actually scattered, okay? Scattered to a very big range. So yeah, this one is probably value for you to calculate. So many things in nature do have approximate normal distribution. Therefore, normal distribution play a key role in statistics. It's actually one of the main assumptions that we actually made for most of the data collection process, where it will follow approximate normal distributions. So that's the reason why later on when you're studying the classes, right, almost all the parametric tests, you need to do a normality test as well, whether the data actually follow normal distributions. When your data follow normal distributions, then you'll be able to use the t-test and ANOVA test and so on, because all these tests have an assumption that your data is distributed in terms of normal. Okay, but if your data is not in normal distribution, then you won't be able to use what we call parametric tests, the t-test and also ANOVA. Then later on, you need to use non-parametric tests, where you actually have an equivalent version of t-test. They have another name. Okay, later on we'll be capturing that one. I'll talk about that one. But main thing over here is trying to tell you that normal distribution is a widely used distribution for in a statistics manner. Right? Then exponential. So exponential shapes looks like this. You have a PDF looks like this, and CDM. And you notice that you see the lambda is actually a bit similar to Poisson. Okay, but exponential is for continuous distribution, but Poisson is for discrete. Right? So the idea is actually the same with your Poisson distribution, where your exponential is actually memoryless. The probability for waiting time is not affected, having waiting a certain time without incident. So this one is actually an example on waiting taxi, you still recall. Okay, waiting buses and waiting taxi is different, yeah? Waiting buses, because the bus have schedule. So in that case, it's assuming that your buses is actually, your schedule of bus is going to come in every 15 minutes. All right. Well, after you wait for 8 minutes, okay, it's very high chances that for the next 7 minutes you will get the bus, you get the next bus. Okay. But for exponential distribution, is the way that they design the distribution is a waiting taxi scenario. Okay, where even though, okay, because the taxi have no schedule at all, you are based on really a random chance that the taxi is going to come. So in that case, right, no matter you're waiting for the taxi for 8 minutes, 10 minutes, 20 minutes, or even 15 minutes, it will not affect your chance of getting your next taxi. Okay, so when you are not so sure about memoryless, next time, waiting bus and waiting taxi example will be able to give you a very good comparison. Okay, over here, train services, but still the same, right? Then there are still other probability distribution, including beta and gamma distributions, but we're not covering. So again, if you want to understand more, there are actually, again, I refer back to Toward Data Science, because there are a lot of good articles over there that you actually can study more. Then 2 more minutes, I just quickly tell you more about this too. Okay, after you've studied about probability and later on statistics is one of the branch for you to actually apply probability understanding. Okay, another one is actually modeling and simulation, where it's actually a place for you to deliver your outcome using the probability outcome, using the probability that you have learned so far, for you to actually simulate. Okay, for example, when you want to build a system where you want to find out, okay, how are you able to improve efficiency in a government hospital, for example. Okay, then you know that this whole government hospital, you have patients, you have nurses, you have doctors, and so on. You want to reduce the waiting time of the patients within the clinic in the hospital, for example, okay, or government hospital. So in that case, right, using probability value that you actually collected from that particular environment, okay, you can simulate it using the probability distribution that we have learned so far in the classes, put it into a computer program, and then you try to model this whole thing and also find out what are the parameters that will actually helping you in reducing the waiting time for the patients, for example. Okay, so this is what one thing that we actually apply in modeling and simulation. If you are more interested, this is the whole second level on probability extensions. Okay, and of course, there's also something called pseudo-random and random number generator that I want to tell you a bit. Okay. Whatever that we have understand so far right now is just a basic probability where my chances of rolling dice is 1/6. Okay, and then every time is 1/6. So it's actually so-called true random. You won't be or somehow independent event. In general, in real life scenario, all the probability is actually independent. Okay, independent in the sense that you don't really affected by your previous event, so, or previous outcomes. But there's a situation where you want this probability to be happening exactly following your calculations. Okay, so one of the example is actually, of course, modeling and simulation. Another one is the one that you actually love a lot. Okay, games. Okay, because every time when you're actually playing games, okay, they have certain kind of situation or scenario where it's actually happening randomly. Okay, but when you're designing the games, you can't always let it to follow true random kind of scenario because in that cases, right, you just put in, or probably it's 1/6. In that case, right, every time when you're generating a random number and then it's not fall into your when it doesn't fall into your so-called probability values, in that case, it can have a situation where your particular design events or design so-called skills will not happen at all. For example, when you're assigning a so-called skills or so-called settings, okay, that is actually going to happen 10% of the time. Okay, but if you're just following so-called true random, okay, you just put 1/10 over there, you put a random number generator and then keep generating numbers. If it's not smaller than 10, then it will not happen. So in that case, right, in the end of the day, maybe you will not happen at all. Okay, because your random number generator again is based on a uniform distributions where it can happen that always your values is higher than so-called 10/100 of it. I'm just giving you a general example. Yeah. So in that case, pseudo random comes in where when you are calculating so-called, okay, you are putting in 1/10 as your initial probability for that particular so-called skill or events and so on. When your first trial, it doesn't happen, okay, it will actually change a bit. Your second trial, right, you will actually having a higher probability, okay, and then the third trial, you have even higher probability, okay, so that in the end of the day, your so-called 1/10 will really happen at least one time at the 10 trial that you actually have. Of course, there's a possibility that your 10%, right, it will happen like fourth trial or fifth trial and then so on. But whenever it happens, you reset. And then once you reset, right, if you try to capture all your memory on your previous outcome to make sure that in the end of the day, when the whole thing goes long run, okay, whole thing goes long run, right, if you're still following 1/10, okay. Of course, right now you all are no longer. I believe you all no longer fancy with Dota 2 anymore. That's why I don't show the example right now because in Dota 2 fan page, right, there's actually a place to tell you how they actually design pseudo random. Maybe you all, if you're interested, you go to maybe right now what are the games or I can see from YouTube. There are maybe Genshin Impact. There are many other games like what is it? Oh, Mobile Legends. All these so-called simulated environment, okay, they are designed based on pseudo-random outcome, okay? It's still based on probability, but you need to redesign the probability so that it will always follow your initial setup probability, like the 10% or 20% and so on. This is what we understand as so-called pseudo-random. If you're interested, that's why I'm putting in extra reading. If you're interested on these two parts, okay, then you please go and find out. Okay, the main thing is over here. Somehow until now we are actually talking about just basics on the probability part. Actually, all this distribution they are actually much more quite useful in many different places. But yeah, that's all for now. So again, this one is actually supposed to be pre-recorded lecture. So I just do one more round, which is a quick 1 hour lecture. I didn't stop much, but if you have questions again, you can actually tell me in the chat, or if you have other like group, if you have group questions and so on, then you can also send me an email again. Maybe you want to follow up or you want to add more content, but I try my best to reply the emails finished by tomorrow so that on Wednesday we can have some discussion on that. Okay, So yeah, that's all for now. Thank you very much. We're gonna reply on the chats later on in text form. Okay. Yeah, that's all. Thank you. Let me go to the. Okay. So yeah. No, that's all. Yeah. Thank you.
Thank you, Doctor.